In this video, I'm going to attempt to recreate the plots in the DoRA paper in Appendix A4. So looking at Appendix A4, they look at the magnitude and direction difference between DoRA LoRA fine-tuned weight and the pre-trained weight of Llama 2 7 billion for the common sense reasoning tasks. And they had these really interesting charts where on the y-axis they have either the delta magnitude, the delta m, or they have delta d, which is the delta of the direction. And they look at every layer. The gray lines are the LoRa base model, fine-tuned models, and the green lines are the DoRA fine-tuned models. And they observe that, there's these different patterns that LoRa and DoRA exhibit. The main takeaway from the paper plots is that DoRA changes less when compared to the pre-trained weights than LoRa does. And you can see, for magnitude, DoRA is down here in 0.02, LoRa is up here, 0.14. For direction, LoRa is up here, 0.007. DoRA is down here, 0.003. So in general, DoRA changes less than LoRa. So I thought that was really interesting, and it was one of the kind of reference points that I had taken away from this paper as, okay, if I fine-tune DoRA or LoRa models and I run these plots, they should look something like this. So they don't provide the exact code that they used for those plots, but we're going to go off of their definitions of delta M and delta D to try to recreate it. And I'm going to reference these equations here. So if I zoom in, here's their delta M, and we're taking the sum and then we're dividing by the dimension. So basically we're taking the average difference between the fine-tuned magnitude vector and the pre-trained magnitude vector. And the important piece here is that K is the output features of the weight matrix. So we want to make sure that we're taking the average accordingly, so it's dividing by K. And then for the directional differences, it's taking 1 minus cosine of the fine-tuned weights and the pre-trained weights, and this is cosine similarity. And I wasn't 100% clear on this next point, but I'm pretty sure that even though it says W0, which is referenced as the full pre-trained weights, I'm pretty sure that these are normalized matrices and column-wise normalized matrices, so that each column is a unit vector, so that the cosine similarity between these two matrices results in values between -1 and +1. And so when we do 1 minus that, we either get 1 minus -1, which is 2, or we get 1 minus +1, which is 0. So the range of this would be 0 to 2. And again, we're dividing by K, and K is the output dimension of the weight matrix. So this is what I'm going off of. And of course, they have some explanatory text which explains it, and I fed that to Claude, as well as giving Claude the paper and the plots, and Claude kind of agreed with the general code that I had come up with. So we're gonna move forward with that, keeping in mind that there may be some implementation details that I don't have correctly done. Okay, cool. So I'm gonna look at the LoRa learns less and forgets less paper's checkpoint, and those models were fine-tuned from the Llama 2 7 billion model. And I'm putting everything on the CPU because I need to make need to make a copy of the base model, because I want to compare the base model weights with the merged LoRa adapter model weights. And the base model here, when you pass it to from pre-trained, it actually overwrites it, and the base model gets rewritten, or I guess replaced with the merged model. I have a video and a blog post about that if you're interested in what that looks like. It was certainly unexpected behavior for me, but it kind of makes sense because it does save memory. Because right now, because I'm copying the base model, I now have two copies of my 7 billion model floating around. So it's using 54 gigabytes of RAM, which is why I need to use a A100. And that's also why it's on the CPU. Okay, so that's kind of the intro. We're going to start with magnitude differences. And I'm just going to look at layer index 0. And we're going to look at we're going to look at the MLP layer for now, but later on we're going to switch that before we make plots to attention layers, because that's what the DoRA paper does. They look at attention layers. And just to go back down there, they are doing Q, K, and V matrices. So if we look at the MLP gate proj layer, the reason I chose this is because it has a different number of in and out features. So we can see clearly we can see which dimension we want to keep, which is we want to get the magnitude one value per 11,008 out features. So W0 is going to be this weight. So I'm going to copy this. And we're going to look at the shape. And this is how PyTorch stores these weights. It's actually out, comma, something you always want to check because, it makes a big difference if we normalize it, across the 0th or the first dimension. So, or I guess the 0th and the 1th dimension. So this is what we have as our pre-trained weights. Now we're going to get our fine-tuned weights, and this is going to be merged model, and it should have the same shape, which it does. Okay, so we can now do the first thing, which is calculate the magnitude vector, and we're going to do that for our pre-trained weights. And we want to do it across this dimension because we want to end up with these many magnitude values. And then we're going to do the same thing for our fine-tuned weights. And if we did this right, this should be 11,008 magnitude values. So what this means is that this tensor contains one magnitude for each column in the corresponding weight matrix. Okay, so that's good so far. And then we're going to take delta M, which is the mean of the absolute value between the fine-tune and the pre-trained weights. And we're going to take the item, and we get 0.047. And right now that doesn't really have too much meaning, but once we plot it, we'll get a better sense of what that looks like. So that's pretty much it for magnitude. Now we do the directional difference. And we're going to do our pre-trained weights normalized, which is going to be across dimension 1. And then we're going to do the same thing for our fine-tuned weights. The shapes are not going to be as informative here because it's just going to be the same shape. And then I forget what this P equals 2 is. So if we look at torch normalize, the exponent value in the norm formulation. So LP. So yeah, this would do the L2 norm, and not L3, but L2. So L2 norm is going to be this guy. Which is x1 squared plus x2 squared square root. But instead of 2 values, we have 11,000 values. Okay, so that's what we have there. But yeah, the dimensions or the shapes of the matrices here are not that informative. So what we want to look at is not that. What we want to look at is show me the first row. What's the shape of this? So this is 4096. So we are looking at one column here. Or sorry, we're looking at the 0th row, and we're looking at all 4096 of our columns. And then if we take the norm of that row, this should be 1, and it is. And so we will have, for our output dimension, these rows all have a value of 1. So they're all unit vectors. So we've basically, removed the magnitude from the weight matrix across our output feature dimension. And we've done that because we captured the magnitude up here. So we can take a look at what this looks like. So we're not going to be doing the mean, but we're going to do the dot product, because for unit vectors, the cosine similarity is equal to the dot product. And we're always going to look at shapes. So good, we have 11,008 cosine similarities, 1 for every output dimension. And then this is going to be 1 minus dot product, and it's going to be the mean value of that. So this is 0.0436. And I think that's everything that I want to do there. I'm actually going to zoom out here and go back to here. And if we look at sum divided by k, so here's our sum, and then taking the mean of the, actually this sum is this one, the cosine vector, and then, or the cosine similarity, and then we're taking the mean of 1 minus the cosine similarity, and we're doing it across the output dimension. So I think that's correct. Okay, so now that we have this, I'm going to wrap everything into a function, and I have my function already written, so I'm just going to copy paste that here. The only difference is now that first I want to grab the module of interest. So if I passed self-attention, then this would get the self-attention module. If I passed MLP, this would get the MLP. And then once I have the module, I'm going to grab the layer name, so qproj, vproj, etc. Take the weight, calculate the delta m, change in magnitude, calculate the delta d, change in direction, and then return those values. And then I have a little helper function here, which I'm also just going to copy paste. And all it's doing is it's creating a list of delta m's and delta d's for each layer in my model. And I give it the base model, the merged model, the layer index. So for llama 2 7 billion, it's 32 layers. So just get that real quick. So here we go, 32 layers. So we're going to iterate through each layer. We're going to pass that layer index and the module and layer name. And then we're going to get the delta m and delta d, append it to the list, and go through all the layers and send back our list so we can plot them. And just to do a quick check, so if I give my base model copy, merged model, give me the 0th layer, MLP module, gate proj, because that's what we did up there, and 047 and 0435 for 36 because it's rounded there because it's 3569, and this should be 047. So yeah, these function, or at least this function is good. And then I'm going to grab this plotting function, which is always verbose, but let me just quickly walk through. I give it a title. I give it the copied base model because I don't want to use the merged base model. I give it a base ID, a LoRa ID, and a number of layers. So it loads in the base model, it merges the LoRa weights, and then I'm focused on self-attention because that's what the DoRA paper uses. And here are the layer names. And then it iterates through each of the layer names, so Q, K, V. It gets the delta M's and delta D's, given my base model copy, the LoRa model, and the other parameters that we already talked about. It does some formatting, labeling, etc. And then I look at the plot. And then I ran this for, I think I did this for like 13 models. So every time I want to delete base model, I want to delete the model to merge, and I want to delete the LoRa model, and I want to garbage collect so my memory stays at around 30 gigabytes. So the only thing that I don't delete is my base model copy, so that stays constant because that's always the same for these LoRa fine-tunes. And then I can run this as many times as I want without crashing my RAM. So yeah, that's basically what I did, and let's look at the results. So I did this for all of the LoRa fine-tunes that were available on Hugging Face from the LoRa Learns Less and Forgets Less paper, all the checkpoints that they published. And first I'll do an overview. So this first slide shows the plots for Magicoder. The second slide shows Open Web Math. Then we have MetaMath, and then we have StarCoder. So unfortunately, we don't have quite the same data set. As this DoRA paper, because they had common sense reasoning tasks, but we can still compare. So it's still interesting to see some similarities. And then for each of these data sets, they provide a number of checkpoints. So they did one with rank 16, rank 64, rank 256. And for Magicoder, they actually published up to 2048. So in all of these slides, we start from the lowest rank on the left and the highest rank on the right. So rank increases as we go left to right on these slides. Okay, so let's take a look. So first thing is, I was blown away that it worked, and I can tell that it worked, or pretty well. Is that okay? These shapes look similar. So the QProj starts out high, plummets, and then kind of slowly increases in a zigzag way. And yeah, we kind of have that shape here. And then we have the same shape for delta D. Same shape for delta D. And then similar shapes for KProj, for delta M and delta D. And we kind of see that a little different, but we kind of see that here. This one was the most convincing, was that the delta M for the VProj and delta D for VProj looks pretty similar. It kind of dips down, then dips up, and we see that kind of similar shape here. So, maybe there's something that I haven't captured correctly, but given the fact that these shapes look pretty similar, I think that's a pretty good sign. And also, this is an unrelated LoRa. This is Magicoder, rank 256, and this was on Common Sense Reasoning. And I don't remember if they said what rank this was, but completely different data set, same model, right? I think that's the important piece. It's the same base model, but completely different data set, potentially a different rank, but it still has this kind of similar behavior. So that was one thing that I want to highlight. The next thing that I want to highlight is patterns within a set of checkpoints for a given data set. So this is Magicoder, and if we look at rank 16, these values are delta M is like 025, 04, O2. If we go up to rank 64, the delta magnitude increases, right? Almost, 10 times. So we're at 0.25 here, we're at 0.12. We're at 0.04 here, we're at 0.15. So, three times there, 4 times. We're at 0.02, and yeah, it's kind of still at 0.02. So it's interesting to see that, like, it's not really clear, or I guess linear or proportional, that how delta M changes for these different matrices. Delta D also goes up from 0.04 to 0.15, 0.05 to 0.15, but then for the V matrix, it's about the same, 0.04 to 0.04. So from rank 16 to rank 64, we had a 4 times increase of rank, and then we had these changes. So when we go from 64 to 256, which is, what is that, another 4-time increase, we don't get the same increase, right? So here's 0.025, that increased to 0.10, 0.12, but another 4-time increase in rank, and the delta magnitude actually drops, right? So it goes from 0.12 down to 0.08. So is there something wrong with how I calculated delta M? I don't know. These curves look correct, or they look similar to the paper. So it's interesting how, proportional differences in rank don't necessarily mean proportional differences in the delta M and delta D. And then we do another, I guess this is not 4 times, this would now be an 8 times increase. And we actually get a much smaller delta M and a much smaller delta D. And for rank 2048, this is actually where we get similar values to the DoRA paper when it comes to delta D. So here we have 007, 009, 009, and here we are at 004, 005. So it was interesting to me that, at least for my calculations of delta D, it took up to rank 2048 to get this type of behavior in terms of the values being similar to the DoRA paper. I hesitate to make any conclusions based off of this analysis because I don't even know if it's correct, but it's certainly interesting that at a much higher rank, the change in magnitude and change in direction relative to the pre-trained weight matrix is pretty small. And I don't know what that means, but I do find it interesting. Maybe because it's a higher rank, it doesn't need to change as much because we have more parameters at play. Maybe, but that didn't really hold for increasing rank from 64 to 256. Other kind of interesting observations, if we zoom out, we can see that the shapes of these, if we look at each row, so Q matrix, K matrix, V matrix, the shapes are kind of similar across the rows. But then if we go here, we now get some varying behavior. So this is now an open web math. And now we get this like dip behavior. We get this behavior here where it plummets and then rises, and plummets and rises here. Here it's almost like a 90-degree L shape. So a little more diversity in the open web math plots. If we look at MetaMath, again, it's a little more consistent when we look at the shapes, and then similar behavior in StarCoder. That's pretty uniform across the rows when we're looking at the shapes of these curves. So yeah, I think I was excited just to get plots that look similar because I didn't have direct code to go off of. So it's pretty interesting to me just on the fact that, okay, even completely different data sets, completely different training setups, but the fact that they use the same base model is giving this kind of signature for the delta M and delta D comparison between pre-trained and fine-tuned models. So does that mean different models would have different signatures? That's certainly something I would want to look into. Smaller models, larger models, what does that look like? What does that mean? I don't know if it means much, but I do think it's an interesting way to see that these models behave in this way. And again, my interest is checking if a model fine-tuned correctly. So if I'm fine-tuning a Llama 2 7 billion on LoRa, I would have to assume that this shape, this kind of general shape would be expected. I would certainly give it a shot and plot it and see if it looked similar. Whether or not that's actually a real signature is, TBD. I don't know if there's other work on that. But yeah, so that's it for this video, recreating the Appendix A4 plots from the DoRA paper, recreating it for LoRA learns less and forgets less checkpoints. I will put this Colab notebook and my plot slides in the video description below, so check that out if you want. And if you see anything in my delta M and delta D code where you feel like there's a mistake and you're able to better recreate these values for the LoRA curves, then drop a comment below as well. Awesome. Thanks for watching, and we'll see you in future videos. Bye.